Students, today in the fifth session of this second lecture series of NGP preparation organized by Indian Association of Physics Teachers, Pune Sub RC 08. I welcome you all for this particular session on today on the statistical mechanics to be delivered by Dr. Sandip Kakade. And one more thing, today with us, Vice President of RC Sub RC 8, Dr. Varsha Joshi Madam is with us. So I request Dr. Joshi Ma'am to introduce formally Dr. Sandip Kakade sir.
Thank you, Kakade sir. I am here to introduce Dr. Sandip Kakade. He is today's speaker. Dr. Sandip Kakade, though you have already been introduced to him for all these days, today as a speaker I will introduce him formally. He has completed his MSc and PhD from Department of Physics, Savitribai Phule, Pune University. He has been in teaching field for last 15 years and is presently working in Department of Physics, SP College. He has received 5 awards for Best Oral Presentation in various international conferences in topics like Advances in Material Science, Advances in Condensed and Nanomaterials, and Smart Materials. He was selected in Avishkar competition and presented his innovative work at state level. He is interested in innovating teaching methods and he has prepared educational videos under the able guidance of Dr. Pandit Vidyasagar. He is in charge of Science Association of SP College presently and he is also working as Secretary of Indian Association of Physics Teachers IPT RC 08C. He has worked as a coordinator of different science popularization programs and national education policy. He has to his credit 11 publications in journals with good impact factor. Now with this introduction, I would request Dr. Kakade sir to start with his presentation. Thank you.
Yeah. Welcome.
Thank you, madam, for your nice introduction. First of all, I am thankful to the Indian Association of Physics Teachers, Sub-Regional Council Pune, for giving me opportunity to share my views regarding the subject on thermodynamics and statistical physics. I am thankful to all of you and also students. Those are giving a positive response and taking inputs from this particular series. So the topic assigned to me is thermodynamics and statistics. So we'll go for that. So basically, as I have seen that the number of questions are there that are not only on the statistics but also on the thermodynamics. So the topic which I have chosen, that is thermodynamics and statistics. So let's start the first topic of our session, that is the thermodynamics. So what is the thermodynamics? So friends, you know that thermo means heat and dynamics is the science behind the motion of a molecule due to the heat. So just we have seen that in mechanics there is a force which is responsible for the movement of body. So in dynamics there is a heat which is responsible for such a motion of molecules. So this in thermodynamics we have to study such kind of motions. So which are the important topics in a thermodynamics? So if you have to look towards these things, then the system and surrounding, that is what the important and significant topic from which our thermodynamics starts. Here systems, we know that the system may be closed system, open system, or an isolated system. The next is macroscopic state and the microscopic states. What is the difference among them? Then the extensive and intensive physical properties and the different examples based on it. Next is thermodynamic process, then the work done in the thermodynamic process, thermodynamic equations of states, laws of thermodynamics, then the enthalpy, Helmholtz free energy, Gibbs free energies. These are associated with the thermodynamics and with the thermodynamic systems. The next significant topic, that is the Maxwell equations. Number of questions are there in all competitive examinations, including the NGP on Maxwell equations. then the specific heat, Mayer's relations, Clais's equations, Clais's Clapeyron equations. These are the few topics which are important in thermodynamics. Now, which are the books you can refer for this particular subject? So, the Thermodynamics by C.P. Arora is a good book. Then the Thermodynamics by Garg, Bansal, and Ghosh. This is also a good book. Then an Introduction to Thermodynamics by Rao Y. Hissi. This is also a good book. Or other books like Max Planck's, then other thermodynamics. These are also good books. You can refer any one of them in which you think that language is good and you are able to understand. So let's move ahead and see basically what is a thermodynamic system and what is a surrounding. So we know that a system is nothing but the part of the universe which are undergoing a study. So here, particularly the system is nothing but a water which is placed in a beaker. So this water is our system which is inside a beaker. And how the physical properties associated with this water inside a beaker, that are changes that we have to see. So here we can see this is a boundary or the beaker in which this water is kept, and this is just a table. So this we call as a system, and this is a table. So these thermodynamic systems can be classified into either open system, closed systems, or an isolated system. So what is an open system? So your open system is nothing but the water is there and the container is open. So if we keep any pot and water in it and it is open, and if we heat it, that means providing the heat or temperature, then what happens? We know that water is converted into vapors, and then what happens? The mass of the water in that particular pot or in that beaker, that goes down. So as well as we consider the temperature, then this temperature of the water will rise. Okay, so the energy associated with that water will also transfer in terms of vapors. So there is a transfer of mass as well as energy will occur in an open system. While if we consider a closed system, that means if we create a boundary, so that what happens? So that whatever the water vapors going out from this beaker, that will be prevented. That means mass of the water which is going out from this beaker, that is prevented. So here this boundary prevent the amount of water vapor which are going outside the beaker, we can say here. So what happens due to it? Due to it, the mass will not be transferred. This mass will not be transferred, but there is a transfer of energy will occur. So such kind of system is called as closed system. Now if we have to see the isolated system, then this is an closed boundary. So we know that we are using the different pots for the tea, or nowadays we also keep the water cold. Okay, so different jars are available in the market. So what is that? That is nothing but the isolated jars using the particular material which do not transmit the energy also. So particularly what happens in this case, mass as well as energy is not transported outside the system, and such kind of system we called as isolated system. Now let's move ahead and see the thermodynamic states. So whatever the water inside a beaker, that we call a system. Now how to define this system? So to define this system, we need some physical parameter. So these physical parameter are just like pressure, volume, and temperature, or we can say internal energy associated with the systems. So all these physical parameter describe the state of system, and this state we call as thermodynamic state. Why? Since basically we understand the thermodynamic properties of the systems using these physical variables or physical quantities. So these particular physical variables or quantities we call as macroscopic parameters or macroscopic systems. Okay, why? Since they determine the properties or all properties of the systems. Okay, well, we have to see what is the microscopic. Microscopic is nothing but the thermodynamics. When we are looking towards the quantum level, that is at the atomic or molecular level, then we need some another physical quantities that can be determined in the particular system. Then that we call as microscopic parameters. So here pressure, volume, and temperature determines the thermodynamic state of a systems, and these parameters are undergoing a change when we are giving a heat to the system. Okay, or heat is absorbed from the system, since the system which we are going to study, that is based on the thermodynamics, right? So let's move ahead. So which are these thermodynamic parameters? As we have seen PPT, and this thermodynamic parameter, thermodynamical variable, we can say, they can be distinguished among state functions or variables and the path functions. So what is the state function first? We know that it depends on initial and final states. So if any physical quantities we determined and it depends only on the initial and final states, then that we called as state function. While if that depends on the actual path followed by an object, then that we called as path function, okay, or path variable. Here it is a state function or state variable. So the next property which is associated with this particular thermodynamics variables is a path dependence. So as I told you, if it depends on initial and final states, then that is the state functions. Now path independence. So this is a path, and if the variables are independent on the path, means we'll see the examples, then that we call as path independence. Then the exact differential equations. So we know that in mathematics, in partial differentiation, double derivative, differentiation of any physical quantity, suppose here it is a function f with respect to y and then x is same as with respect to x and then y, then that particular physical quantity we called as exact differential equations. Next is Euler theorems. So here we are just changing the constants. So delta x upon delta y at constant z into delta y upon delta z at constant x into delta z upon delta x at constant y, and this product is equal to -1, and this particular theorem is called as Euler theorem. So here we can change this x, y, and z. These are nothing but our thermodynamics variables. We can replace this particular mathematical terms using our thermodynamic variables, and we can see that whether the system follows this Euler theorem or not. Next is cycle integral of this particular state functions is 0. Then the examples are there: pressure, temperature, volume, internal energy. These are the different examples of this particularly state functions. Now the question is there that which of the following is not an exact differential equation? So we know that du, ds, df all are exact, but dq, that is heat provided, is not an exact. Why? Since this will not obey this law. Okay, so this is not an exact differential equations. Or we can say that heat is q or work done is also path function. Okay, and that's why they are not exact. Okay, this if path is changed, then that will change. So depending on these particularly, we have different examples. They were asked in NGP. So the question that is asked in NGP is that in a thermodynamical process, which of the following is or are integrable, that is a path independent function or a state function? So we can say particularly the answer is what? The options are amount of heat, internal energy, enthalpy, and entropy. So let's see the what is the amount of heat. Heat is nothing but whatever the amount of heat is given to the system or absorbed from system. Internal energy is nothing but the internal energy associated with the system. Temperature characterize the internal energy, and enthalpy is what? It comes from the Greek word that is heat inside. So whatever the heat associated with the system inside it, that we call as enthalpy. So actually the formula for dq and dh is somewhat similar, but what is the difference? Basically enthalpy is associated with the heat inside, while amount of heat is associated with the heat given or absorbed. Now the next physical quantity, that's entropy. We know that the energy which is not available to do work we call, or use energy we can say indirectly, so that we call as entropy. Okay, so how much heat is added or removed, okay, that can be given in terms of enthalpy, but dq is actually the heat added or removed. So this is what the enthalpy. Now we have to see that what is this question particularly, which of the following is an integrable or path independent function. So we know that what is this dq, it depends on the path, as we have seen, or entropy, it also depends on the path. If we change the path, then what happens? The time required, that will be the different, and accordingly what happens, the amount of heat absorbed or evolved, that will be the different. The entropy is also different. But if we consider the internal energy, that is a state function, it is path independent. And enthalpy, as I told you, enthalpy is what? It is nothing but the heat inside, so it remains as it is of that particular object. So these particular two quantities we call as an answer, that is b and c, that is these are the path independent, or we call these are the state functions. Now let's move ahead and see some particularly the first law of thermodynamics. So what is the first law of thermodynamics? If you change at constant volume, it's called as internal energy. That the amount of heat is provided, that is utilized to raise the internal energy of the systems, and next then it is utilized to do the work. So that means dq is equal to du plus dw. So if you provide a dq amount of energy, then it is the sum of rise in internal energy of the system and then the energy which is utilized to do the external work. So that we know. So dq is equal to du plus dw, and du is nothing but here E is the another symbol is utilized. We can say indirectly d is equal to dq minus dw. That much internal energy change is associated with the system due to the supply of this much amount of heat. Now let us see the different formulas associated with the work done. So if we are giving a heat, then work will be done by the system. So the work done by the system is given in terms of either product of force into area, or it can be given in terms of pressure into area into the length, or we can say it is in terms of P into delta V, that is constant pressure, the change in volume, or it is plus minus P into V2 minus V1, or work done may be positive or it may be negative. Okay, work is done on the system, positive, work is done by the system, it is negative since internal energy goes down. Work done for an isothermal change, that is delta T is 0, that is also we know. Then there is what? Hydrostatic system. Here work done is given in terms of W is in terms of integration of PdV, stretch wire, W in terms of integration of T into dl. Regarding the surface tension, we can calculate the work done. Liquid film, gamma into dA. So electrochemical film, W is equal to E into dq, or dielectric material, here W is equal to E into dp. Okay, so here is van der Waals gas equations, actually using which also we can see that W is 2.303 ln of V2 upon V1. In that particularly real gas, we can calculate the work done. So let's move ahead. So these are all different formulas associated with the work done. I'm not going details of theory since this particular series is organized to help you for the NGP preparation, and it is expected that you are well known about the theory part. So I will give more stress on the numericals and problems, and the theory associated with that I will explain time to time. So now let's see another example based on the internal energy and the work done. So what is the question? That a given quantity of a gas is taken from state A to state C. This is the state A and this is state C, reversible by two paths, A to C, and another path is A, B, C. This is the two. These are the two paths here. This is a reversible reaction occurs. And the system changes from A to C along AC, or it may go from A, B, C. Now during the process AC, the work done by the gas is 100 joule, and the heat absorbed is 150 joule. So during the process of AC, we can say 100 joule of work is done and 150 joule is it absorbed. If during the process of ABC, the work done by the gas is 30 joule, here work done is given along this path. How much is the heat absorbed? That is what the question along this path. So according to the given physical parameter, we can say that du is equal to what? dq minus dw, and using it, what we can write, that is equal to, here amount of heat is given, that is 150 joule, and work done is 100 joule. So the total internal energy which is associated at point C is equal to how much? 50 joule, right? Now internal energy is a state function. So though the system comes from A to C by this way or by this way, still internal energy remain constant. So I can use this 50 joule of energy in this equation here along the path of A, B, C. Then the dq is equal to du plus dw. That says first law of thermodynamics. Put this value, that is 50 joule here. So that is 50 plus, now the work done along this path is given, that is 30 joule. That value just I have substituted, and it gives the dq, that is equal to 80 joule. So along the path A, B, C, 80 joule of heat is given to the system or absorbed by the system. Okay, that is the required answer. Let's move ahead and see the another physical properties associated with the thermodynamic variables. So they are the intensive properties and the extensive properties. So what are the intensive properties? So these are independent on the amount of substance. Then that property we call, or that physical parameter or quantity we call as an intensive property or intensive physical quantity. And another physical quantity which is associated with the system, that depends on the amount of substance, and then that physical quantity we call as extensive physical quantity. Okay, so example of intensive property or intensive physical property is temperature. That is, T is not equal to T1 plus T2. That means if I have a beaker of two different temperatures in water in that, suppose 30 and 70, then what happens? That if I mix that both the liquids, then the temperature will not become 30 plus 70 is equal to 110. Okay, but that will be the mean of that one. So that means T is not equal to T1 plus T2. So in that, particularly this kind of thing we call as intensive property. While if that beaker is there and the volume is suppose what 50 ml and another is 75 ml, then the total volume becomes 125 ml. So that means the volume is extensive. It is additive property, while temperature is not an additive property. So which are the different properties we call as an intensive property? So the molecular volume, pressure, density, chemical potential, dielectric constant, pH, these are all intensive properties. While heat capacity, number of moles, Gibbs free energy, Helmholtz free energy, internal energy, and entropy are the extensive properties. They depends on the amount of substance. That means they are the additive one. If I add one substance into the another, these properties will become double one, or depending on the amount added in it. Okay, while these properties will not get added, but they will find the mean of that one. So let's move towards the problem based on this extensive and intensive property. So here the problem is that two gases separated by an impermeable but movable partition are allowed to freely exchange energy. So two containers are there, and we can say the gas is there, and it is what movable partition is there, but it is impermeable, and energy exchange is allowed. At equilibrium, the two sides will have the same. So as I told you, what happens at equilibrium? What happens particularly? The volume is an additive. Okay, so at equilibrium, what we can say, we will have the same pressure and temperature, or will have same volume and temperature, or will have same pressure and volume, or we have same volume and energy. So as I told you, what happens, volume is an extensive property which is associated here. So this will not be the same, that is an additive one. So the physical property which remains same after means that can be transmitted after this partition, since so that what happens, temperature of both the side will become same. While volume if you consider, then that is an additive one. So pressure also remains same. Pressure and temperature is the first one, that is the answer. Now the second is viscosity and surface tensions are. So the question is given, both are intensive variables, options are there. Both are extensive variables, intensive and extensive variables respectively, or extensive and intensive variables respectively. So we know that viscosity and surface tension, if I add one liquid into the another liquid, then viscosity of both the liquids will not change. They will create two separate viscous layers. Okay, so as they create two viscous layers, and viscosity is not going to change. Similarly, in case of a surface tension, it will not going to change, since that is an inbuilt property of that particular liquid. So both are we call as an intensive variables. Okay, they are intensive variables since we are measuring these particular properties of that particular liquid. Next is, so there are different thermodynamic processes. So we can, according to the different change in physical parameters, we can say they are the isothermal process, isobaric process, isochoric process, adiabatic process. So in this case, we know that temperature remains constant. So PV is constant. It's the Boyle's law actually. Isobaric process, P upon T is constant. Isochoric process, that is P upon T is constant. Adiabatic process, PV ratio gamma is constant. And accordingly, using the first law of thermodynamics, we can develop this relation that if delta U0, delta Q is equal to delta W. Since there is temperature is constant, that means it is characteristics of internal energy. So delta U0, delta Q is equal to delta W. Now this is another for isobaric. This is another relation for isochoric, since volume is not going to change, and delta W is P into delta V. So we can say delta Q is equal to delta U. Adiabatic, here delta Q is 0. No exchange of heat occurs. So delta U is nothing but the work done. And the another process is also mentioned here, that is isentropic processes. So here entropy remains constant throughout the process, or that we call as isentropic process. And then next is polytropic process, so which obeys the Boyle's law, and actually all these laws are constant throughout the process. Particular one. Now let's move ahead and see some numericals. So here it is an adiabatic process and thermodynamic first law based on it. We know that work done is PV raised to gamma, or if we use the different parameters, it becomes TV raised to gamma minus 1 or TP raised to 1 minus gamma is equal to constant. This is based on this, different numericals will be there. So to study this particularly, it's needed to draw a graph, then that becomes easy to understand. So isobaric means constant pressure. We can say isothermal means here this is the one. Adiabatic means this is the one. PV raised to gamma. It moves towards the V side. Okay, slope. So these are all the nature of this work done. Now the question is there in equation of a state for a gas with internal energy U is given, PV is equal to 3. Then equation of a state in adiabatic process is equal to what? So we just use first law of thermodynamics, dq is equal to du dw, and use that U is equal to thrice PV, so 3 PV, and integrate it to calculate the du, 3 PdV plus 3 VdP plus PdV, and as adiabatic one, so dq is equal to 0, put that, and the solid, then what it gives you? It gives you PV raised to 4 by 3 is equal to constant. So this is the adiabatic process, and for that the equation of state will be PV raised to 4 by 3 is equal to constant. So this is the answer. Okay. So just we have utilized the first law of thermodynamics and the concept of adiabatic process. Let's move ahead and see the other important topic which the questions are coming, that is Carnot engine. So we know that Carnot engine is what? It is theoretical thermodynamic cycles proposed by Leonard Carnot. And according to the Carnot theorem, the reversible engine will always have a greater efficiency than the irreversible one, obviously. So the Carnot cycle achieves a maximum efficiency because all the heat added to the working fluid at a maximum temperature. And Carnot engine is an idealized version of a heat engine that involves a reversible cycle. It is known as Carnot cycle. So we know that Carnot cycle is a reversible cycles, and it is an idealized version of a heat engine. So what is the idealized version? That means no heat loss, okay, and that's why efficiency is maximum. So this heat engine is proposed by Carnot, and that's why it's called the Carnot engine. And based on Carnot heat engine, we have a number of questions in the examinations. So to study in details, actually, the mathematical formations are coming up as derivations of it. So that is work done. So actually the system goes from A, and now it is reversible. So it again comes to the A. So we can say A to B, B to C, C to D, and again A. So A to B is an isothermal expressions. We can say then B to C is adiabatic, sorry, isothermal expansion, adiabatic expansion. Since volume is increased towards this side, okay. Here it goes down, compressed, here it compressed. So what this indicates? This indicates isothermal expansion, adiabatic expansion. Then this is isothermal compression and adiabatic compression. So isothermal means temperature remains constant, and adiabatic means heat will absorb or evolve. So accordingly, we have different formulas for the work done for these different processes, and we can have a different. Actually, we have a formula which is generated the efficiency of a Carnot engine, and it is given by Q2. We can say in terms of heat, we can say Q2 upon Q is equal to 2 upon T1, or efficiency is given by 1 minus temperature upon sink, temperature of sink upon temperature of source. So 1 minus T1 upon T2, or what we say it is we can say Q1 minus Q2 upon Q1, or it is T1 minus T2 minus T1 upon T2. Okay, in terms of temperature, since they are the reverse one. So the question is there based on it. The simple a reversible Carnot engine is operated between temperature T1 and T2. If T2 is greater than T1 with the photon gas at the working substance, the efficiency of the engine is. So how much is the efficiency of the engine? Just it is 1 minus T1 upon T2. As I told you, it is what? Q2 minus T1 upon T2, or Q1 minus Q2 upon Q2. So here just we have to utilize this particular formula. Next is a Carnot. Based on this Carnot engine, again we have another one, that is a Carnot cycle operates on working substance between two reservoirs at temperature T1 and T2. Here T1 is greater than T2. During each cycle, an amount of Q1 is extracted from the reservoir T1, and Q2 is delivered to the reservoir T2. Which of the following statement is correct? So Q1 is gaining amount of energy, and Q2 is giving. So what is work done? Q1 minus Q2, as we know. Or what is the formula for this? Q1 upon T1 is equal to Q2 upon T2. Just we have seen. So this is also correct. This is also correct. we have to see which one is incorrect. Right? So entropy of the water reservoir decreases. This is the statement. And another one is entropy of the universe increases. So you know that very universal statement. Entropy of the universe increases. It will never wrong. So what is the wrong? Entropy of the hottest reservoir decreases. And we know that entropy will not go down. It always increases. So the entropy of the water reservoir decreases. This is what the wrong statement. So based on this only for logic and using the Carnot theory, can say that is the wrong statement. Now the next question which is asked in GP, that is, no engine can be more efficient than the Carnot engine working between the same limits of temperature. Proof. So it is a very simple. Why? Since Carnot engine is an ideal one, and in this engine what happens? It is a lossless, frictionless, and there are no temperature difference in the heat exchange process. So this kind of difference will not be generated as heat is absorbed or is equal to evolved is equal to absorbed. So this is an ideal one, while this ideal condition will not be have one in a real engine. So it is impossible to heat engine to achieve this 100% efficiency according to the second law of thermodynamics. Okay, so what happens? The wastage of heat will occur to the different thermal process, and that's why. So just we have to say that how it happens. Another question on based on Carnot engine, that is 1000 kilocalorie of heat at 627 degrees Celsius and exhaust it at 27 degrees Celsius, then the efficiency is equal to how much? So you calculate the utilize the formula, then what happens? Eta is equal to W or Q1 minus Q2 upon Q1. So this gives you T1 minus T2 upon T1. So this is equal to how much? This one. So this gives you the formula. The answer of efficiency that is here. So this is correct. Then eta work done is equal to eta into Q. So this gives you the value 2.8 mj. That is also here. So that is also correct. Next is W. So work done in terms of this another unit, that is kilowatt hour. Just we need a conversion. If we convert it, that is going to be this one. So this is also correct. If we use W and we use just different units they have utilized, and they told you that which one is correct. But most of the times what happens, one answer is correct, we are going ahead and not going for the another answers. So here you also have to for the another answers and purposefully keep the different values, but the answer is same. Just change unit you have to do. So that gives you MEV. So all the answers here can correct, and so that's why we can say the efficiency all correct. Okay, let's move ahead. So heat engine. So as I told you, what happens in a heat engines? Source work done from sink. We can observe the energy from source is given and source is taken and given to the sinks, and work is done. So E is equal to Q1 minus Q2 upon Q1, or we can say 1 minus T2 upon T1. Now here, these are what the different physical things for the heat engine. And in case of a refrigerator, what happens? We need an external agency to do work against it. So here K is equal to coefficient of performance, and which is Q2 upon W, Q2 upon Q1 minus Q2, that is equal to T2 upon T1 minus T2. And if we based on this, we can say coefficient of performance is just 1 minus efficiency, or efficiency also we can calculate from it. So based on this T1 upon T2 is equal to Q1 upon Q2, we have this kind of example that just the temperature is given, that is 1000 K, and takes it at 600 K. So T1 and T2 is given, and engine operates at a maximum possible efficiencies. The amount of work performed by engine for 200 joule heat input is. So what they have asked you, if the engine work done, that is in terms of, so work done is nothing but what the particularly we can see in terms of heat here. In case of a heat engine, this whatever the amount of heat is provided, that is utilized to the work done. So that's T1 is given, T2 is given, Q is given, and just Q2 you have to calculate, and that gives you the value of that particular work done in joule. So just T1 upon T2 is equal to Q1 upon Q2 is the required answer, that is 800 joule. Let's move ahead and see the another law of thermodynamics, that's thermodynamics second law. And what is this law? These are the different statements using which we can state thermodynamics second law. So this is the this is also significant one, and the important statement is we can't design any device which heat transfer from lower temperature to the higher temperature, the doing external work. So based on the refrigerator works actually, since we need external work, and so that we can transfer the energy from cold reservoir to hot reservoir. So the refrigerator, though it is cold, still we have to take energy from inside it and we have to give to the other atmosphere that higher temperature. For that we need electricity. So this is the example of uh, thermodynamics second law. And what is the question? This the entropy is defined in the state function defined in terms of dq upon t. Then for reversible it is 0. For irreversible process it is always greater than or equal to 0. So another question is there, that is for dq. If the entropy of a system remains constant in a thermodynamic process, the process is hot, isotropic, isochoric, isothermal, or adiabatic. So it is a very simple. We know that if entropy is constant, then ds is equal to d. We can say ds is equal to dq upon t, or dq is tds. Now ds is 0, so the process is adiabatic since it remains constant, either it get absorbed or evolved. Let's move ahead. So this is what the formula, as I told you, this is the integration of dq upon t. This is the entropy, and the amount of heat is given to the system at constant temperature to convert phase from one phase to the another. Okay, that we call as latent heat L. Now TS diagram is there. This is also an important diagram if you have to study the entropy. So net work done is nothing but always area under the curve, or the divided. So Q1, Q2, and Q3. Now it is this direction, so treated as a -1 minus, and the amount of it is given is Q1 plus Q2. Q3 is just Q1. So this area enclosed by the current TS diagram for total area. And the latent heat is nothing but energy absorbed or released when there is a phase change at constant temperatures. So based on it, we have a question that when 100 gram of ice at 0 degrees Celsius melts, the change in entropy is in calorie per Kelvin is about how much. So just we use delta S is equal to hot L upon T, and we can use 100 upon 80 into temperature is 0 degrees Celsius, that can convert it into Kelvin, and you can write the answer. So we have these answers actually. It is that is 29.3 calorie per degree Kelvin. So let's move ahead, and we have another example based on this also. Two systems with huge capacities and entropy C1, S1, and C2 respectively interact thermally and come to a common temperature T up. The initial temperature of the system 1 has T1. What are the initial temperature of the system 2, T2? And the net entropy change of the combined systems. So here heat given is equal to hot, heat taken. Now those systems are there, they are in contact with the third systems, which is at temperature T. T1 is giving heat, T2 is taken, heat taken. So we can write C in terms of C and T. We can write C1 TF minus T1 is equal to C2 2 minus TF. From which we can write T2 is equal to C1 upon C2 TF minus T1 plus TF. And just if have to calculate the entropy, it is integration of delta T, particularly the TQ upon T. So in terms of this C1 and the C2, we can write here. So we can write C1 T1 to T dt upon T plus C2 TF to T2 dt upon T. Since here is the another system which is in contact with this, and just we use that C1 ln of Tf upon T1 plus C2 ln of T2 upon Tf. And if we simplify this will give the answer, that is T2 raised to C2 upon T1 raised to C2 ln of this into T raised to C1 minus C2. So this is the answer here, C. So let's move ahead, and here is another question. So again, the change in volume in atoms of an ideal gas enclosed in a container of a volume, the volume of a container is changed to 4V. So just entropy is calculated in terms of minus n kb ln of V. This is a V1 upon V2, and thus delta S is described. So it gives you n kb ln of 4. So just 2 raised to 2. So 2 comes here. So they have asked you that in units of n kb ln of 2, how much is the value? So in terms of n kb ln of 2, it is a 2. Now the next question, that is entropy, is given, and what they ask you that the probability of alignment in upward direction is the value of P at which the entropy is maximum. So we know that for maximum entropy or maximum function is maximum when its first derivative is 0. So just you can see this use first derivative, and from which we can say that P is equal to 5. It means first slightly to cover all the parts. So enthalpy is a state function. As I know, you know that enthalpy is a state function we have discussed. So it is a path independent. So it is equal to U plus PV, and delta is measured generally. So this is just regarding enthalpy. This is regarding the Gibbs free energy. It is an extensive property. It is a state function. G is in terms of H minus Ts. Written dg is equal to Tds minus Tdv. These are all Gibbs free energy properties. Okay. So let's move to the significant part in thermodynamics on which the general equations are there, and they are the Maxwell equations. So they are based on all these energies. So we have different energies. First one is the internal energy du, then the Helmholtz free energy delta H or delta A, or we can say A. This is also denoted by H. Okay, so A is nothing but this H. This H is same as like this A. Then enthalpy H is equal to U plus PV. Then Gibbs free energy G is equal to U plus PV minus Ts. That is dq minus Q minus Ts. We can say. So if you differentiate them, then we got this kind of relation that du is equal to what? Means dq is ds. So just I substitute here, and dw is pdv. So du is equal to tds minus pdv, or dh or da is equal to minus pdv minus sdt. Just using first law of thermodynamics, we have to substitute the value of du. Okay, and dq, then that will give you two values, and we have to use the second law of thermodynamics, that is dq is equal to, sorry, ds is equal to integration dq upon t. Okay, so that will give you this. Then dh is equal to tds plus vdp, or dg is equal to vdp minus sdt. So just if you use first and second law of thermodynamics, we'll get all these equations. And from these equations, we can build these Maxwell equations. These equations are called as Maxwell equations. Okay, that they tell you that which physical parameter will change with respect to another physical quantity, then what the another physical quantity will be generated. For example, here internal energy changes with entropy at constant value, it will give the temperature. Okay, so how to derive these things particularly? So here is one very important diagram. Okay, and actually a very good statement that good physicist here studied under a very fine teacher. If you keep in this mind, and if you do arrangement like this, you can write any of this particular physical term. So just we can see about the dg, suppose. So what happens in case of a dg? The changes here dt, here it is dp. So I can write here dt, okay, and here is dp. So means along this line, where the physical parameter comes, that change, in that change you have to write is dp and dt. Now what you have to write? You have to write another one. So with respect to p, which is another means in front of p, another physical parameter is v. So you can write v into dp. Okay, and in case of just now what I told you, dt is minus. Why? Since it goes down, so minus dt. Now just in opposite of t, that is a s. So I just substitute s. So vdp minus s dt. That means, or we can say another example also. So let us see dh. So what is on dh axis? dp and ds. So I can write in terms of dp and in terms of ds. So dp and ds. Now ds is right hand side, dp is upper side. So as per mathematics, what happens? Or logic, upper and right hand side terms are positive. So ds is positive, dp is also positive. Just you have to see the opposite term p. So it is a v. The opposite term of s is t. So v is associated with dp and t is associated with ds. So you can write this ds equal to tds plus vdp. You can play with it, and you can write any of these particularly, you can say, the equations. Okay, these equations, and again you can come towards this one. So like this, we can just have to differentiate t is equal to dA by u upon dA by s when v is constant. Or suppose if we have to calculate dA, so then what happens? If we have to find in terms of p, then p is equal to dA by a upon dA by v, and you have to keep this temperature constant. So this factor becomes 0. So p is equal to minus dA by a upon dA by v at a constant t. Or here if you have to calculate this, then d, then sort of volume, then how do we calculate this? dh upon dp at constant t, since sorry, at constant s, since s is 0, then we use dh upon dp and the value is v. Okay, it is not dh, that's partial differentiation, that is dh upon dp. Okay, so all these Maxwell equations can be obtained, okay, using this particularly simple way. Let's see some examples based on it. The free energy of a thermodynamic system is given in terms of F is equal to U minus Ts. So dF is equal to, I can write du minus Ts minus S dt differentiation. But we know that what du, TdS, and all that, just we can use dF is equal to what du minus du plus PdV minus S dt. Okay. So this is TdS is what? Particularly work done. Sorry, dq, and dq is equal to du plus pd. Okay, so this is what dq, and ds is equal to dq upon t. So for this particular term we can use du plus pdv. So du minus du plus pdv minus s. So this gives you df is equal to minus pdv minus s dt, and this is a Helmholtz free energy, and this is the maximum amount of useful work that can be extracted from thermodynamics closed systems at a constant volume and temperature. So which terms are remaining constant? dt and dv. So this gives it. So let's move ahead. Which among the following set of Maxwell equation relation is correct? So to understand this, what we have to do, so this answer is B, but I will not go in this derivation. The question may become in another physical parameter also. So just you have to keep in mind this particular diagram, and you have to write these equations. If you write this equation at once, just bring this particular term here. This is a constant as a suffix. This will give you another parameter of this particular one. So in this way, you can do this one. So another question, that is energy is given where B is a constant and other symbols have their usual meaning. The temperature of the system is equal to how much? This is the question. So just use the law, that is TdS. Okay. Now what we can use here, particularly the temperature of the system is equal to, that is what the question, TdS is equal to dE plus Pd. We can calculate, and we can write this. Here it is. That is in terms of your first law of thermodynamics and second law of thermodynamics, that gives you T value. So this differentiation gives you the answer. So let's move ahead and see another example. That is for an isolated thermodynamical system. PU, TVU, S and F are the pressure, volume, temperature, internal energy, entropy, and energy respectively. So these are the meaning. So we know that dF is equal to minus S dt. So just PdV. So we can write here delta by upon delta T is equal to minus S, the simple thing. The curve OA in the PV diagram represents the reverse of final state. So particularly expansion is there. So now volume particularly that this value will remain constant. So what happens as gas is expanding, pressure will rise. So the point will be here. So next is a thermodynamical identity relates the variables P, V, T, and S on the ideal gas, that is TdS equal to this particular equation. This we call as first TdS equation. So to develop this equation, actually depend or depend, they ask you. So we can depend it. So entropy is given in terms of P and T. We could differentiate, it gives you this relation. Okay, at constant volume at constant temperature, multiply by T, it gives you. Just you use the second law of thermodynamics, that is dq is equal to TdS, that is equal to Cv into T. Okay, and this gives you that is Cv. And if you use these mathematical equations, then this gives you first law, first TdS equation. Okay, so this one. Similarly, we can calculate, we can derive another second TdS equation, that's TdS is equal to Cp. Sorry. So TdS TdS is equal to Cp dt minus T into delta V upon delta T at a constant P into dt. So these are the important physical parameters that this gives the values of pressures also. So what is this pressure and temperature relation? This is a significant one. We know that at the ground level, this B is called as boiling temperature, we can say, suppose. So at the ground level, pressure is maximum So boiling point is higher, and that's why we can prepare a food easily. But if we are going towards the mountain, then what happens? Pressure goes down. If pressure goes down, then what happens? Easily that water gets evaporated, and so food will not be ready or it will not be cooked. So we need to use a pressure cooker. So such things are required. So this is the third of thermodynamics. The entropy of the perfectly crystalline substance at absolute 0 degrees is 0 Kelvin. Okay. So this is again the entropy in terms of what different examples. This is NCV ln of T2 upon T1. This is integration delta S is NCV integration of dt upon T. So the integration of T is ln of T, and with the integrals T1 to T2, you can write this one, and we just put the formula values and that will give the value answer. Okay. So again, this is the similar relation. We just substitute the this particular one given value of this CP, that is 5 plus 0.1 T, and just calculate. Okay, just I have not written here the problems, but you can do this integration. So small things are required to calculate the answers. Just integration is important since the second of thermodynamics is in integral form. So that's why we need to calculate the integrals. Now, van der Waals equation is given, and at a critical point where all the roots of the above cubic equations are generated, the value is given by. So just few values they have asked. So use this equation, differentiate, and with respect to value, first derivative is 0. Okay, and the second derivative is also 0. So it gives value is 3 for critical value. Okay, obviously. This, we know that maxima minima conditions in the mathematics. For critical volume, the expression with respect to volume, first derivative and second derivative is 0. So thus that gives you the critical volume, that is 3b. Now another question is there, that is the temperature of inversion is the emplacement of heavy gas opening van der Waals equation is 12 states boil temperature, support or input. Thus they are thinking that you have gone through it or not. If you are not read it, you don't know, and you cannot write the explanation for that. This is just they want to see that whether you know these things or not. So the answer is what? For gas opening van der Waals gas equation, this is the temperature of inversion. What is temperature inversion? It is when the temperature at a certain layer of atmosphere stays constant. Sorry, it rises, then that we call it inversion temperature. And this gives you Joule-Thomson coefficients, that is dT upon P at constant age is equal to -1 upon Cp to say upon RT minus B. And your boil temperature is nothing but the temperature at which gas behaves like ideally. So that explanation you have to write, nothing else. Next is a velocity distributions. Okay. So these are what different velocities. We can say using the most probable velocity, average velocity, RMS velocity. RMS velocity is what? It's a square root of mean square velocity. Or most probable velocity is the velocity of maximum number of gaseous molecules. Okay. So these formulas you can type in theory, and we are calculating the RMS velocity. So why the RMS velocity is important? Since average velocity, we can say the net velocity due to the random motion in 0, and that's why the average velocity is required. Next is Maxwell velocity distribution. So one dimensional, two dimensional, and three dimensional. In one dimension, you can say this is square root of kt upon n. In two dimensional, it is square root of 2 kt upon. In three dimension, it is square root of thrice kt upon m. So you have developed relations in theory. So it's just for revision. Means the questions will come on this particular formula. Then you have to write the answer. The question is on Boyle's law that can be expressed in a differential form. So we know that PV is equal to constant. So we just differentiate with respect to pressure. That gives you dV upon dP, and that is minus d upon P. Just differentiate this particular equation, that is P into delta by PP. That is P into delta V upon delta P plus V. Okay, since delta V upon delta P is 1, that gives you the condition. Since Boyle's law is written in terms of P delta V upon delta P. Let's move ahead and see some example on latent heat. 10 gram of ice at 0 degrees Celsius is added to a beaker containing 30 gram of water at 25 degrees Celsius. What is the final temperature of the system when it comes to a thermal equilibrium? Is the question. So the specific heat of water is 1 calorie per gram per degree Celsius, and the latent heat of melting of ice is 80 calories per gram. So just we can utilize this particularly given equations, and we know that Q is nothing but m into L. Okay, just we have to substitute the mass and L. Just we have done this in theory in particular slides. M into L. So what is this m given? That is 10 gram of ice. It is mentioned here. And what is this? 80 calorie of heat is mentioned here per gram. 1 gram. Now this is 80 calorie per gram. So 80 into 10 gives you total heat. Okay, so, which is actually we can say this much ice is mixed, so this much it maybe what happens that 10 gram of ice is added in beaker, that this much heat is there associated with the beaker. The amount of water is added in that beaker, that is 30 gram at 25 degrees Celsius. So again Q is equal to what? M into CV into T, since we know that specific heat. So M is equal to what? 30 gram of water. Then Cv is equal to 1 for water, that is mentioned here, 1 per gram per degree Celsius. 25 degrees Celsius is there. That is the temperature of water which is added. So that gives you the value of Q. And how much? 750 calorie. So what this indicates that ice, latent heat of ice, suppose is 800 calorie here. This is particularly the amount associated with that ice in the beaker is 800 calorie. And with water which is mixed, that is 750 calorie. So and the question is that what the temperature of the system if it comes to the thermal equilibrium. So as this energy is not sufficient, so that system will not come into thermal equilibrium. So or whatever the temperature associated with that 0 degrees Celsius only. And another important equation, that is Clausius-Clapeyron equation, that is dP upon dt at constant V is equal to L upon T into V2 minus V1. On these equations, always there is question like Maxwell equations, single question will be there on this particular Clausius-Clapeyron equation. And questions are not difficult, just need to use the formula and use to substitute the values. Okay, just I can see here this is a rearranged in this particular equations according to the given terms. So P2 is equal to Q L upon V2 minus U1 to L of T2 upon T1, and just what is given according to the given terms, we have to use the values. I will not go into this, okay, but just the magnitudes are given, temperature, pressure, and then this is atmospheric pressure, temperature is also given, T1 is given, T2 is given, then here pressures value kilogram, 1000 kilogram per meter cube, that is given. Okay, density are given 34 kilogram per meter cube, these are the respectively. So we use just substitute in this formula and calculate it. So what is the use of this particular equation? It can estimate the vapor pressure at another temperature. If know the vapor pressure at some temperature of that particular specimen. Okay, so this is a significant equation to understand the vapor pressure at another temperature. So generally the question will come on and will ask you the vapor pressure at another temperature only. Let's move ahead and see the similar question in NGP 2012. But they have asked, they have given such kind of things. Now it's a simple one. So since L is given and just they ask you to define it. Okay. So justify and explain the meaning. So that is given 800 minus 0.705 T. So just we can calculate dl upon dt from it, and we substitute here. So dl upon dt formula is substituted. Water value is given. Okay, and dl value is 800, and this is what happens. This is the saturated water vapor. Temperature is 273 plus 100 degrees Celsius. That is 373 degrees Celsius. So that gives you C vapor. That is the specific heat of a vapor. Okay, that magnitude can be calculated using this equation, using the Clausius-Clapeyron equations. I will not go in details, but this you can calculate it at another temperature. So the boiling and melting point of liquid changes pressure is explained by the equation. Which expression explains the boiling and melting points of the liquid and changes with the pressure? So the similar questions associated with the Clausius-Clapeyron equation, and just can be explained using it. Okay. So but here means actually just we can rearrange this equation, and the equations, all equations are going to be correct, but while here it's not of correct Maxwell equations, and so there is will be positive symbol, so it is incorrect. Next, it is known that 1 gram of water freezes as this much of ice, and the pressure at which water freezes at -1 degree Celsius instead of 0 degree Celsius is equal to how much? So this is a very simple questions. Can use the classical electron equations, and dT is equal to how much? -1 degree Celsius that they have given. We can use the value of L. That is dT. We know that water it is 4.2. That means 4.2 into 8 into 10 to the 3 joule per gram. Use this value L. L means your temperatures are given. Okay, is given -2. Then V2 minus V1 is given. That is minus 1.1 minus 1.01 gram of water, which is at this much cc of ice. Okay, so we can calculate that particular volume using mass, and finally the answer. So the another significant question is with the quantum consideration. The specific heat is a temperature dependent property of a substance. Draw collectively an appropriate plot of a variation of the specific heat of a dynamic gas of a temperature range from 30 to 5000 K and explain. So specific heat of water you have to calculate and at different stage. So actually I have particularly purposefully mentioned definitions for the students those are at F5 level. So the normal specific heat of a gas is thought to be independent temperature, but what happens, they depend, means the particular values are given in terms of its total energy associated with the atomic molecule is translation plus rotational plus vibrational, and the specific heat also can be written in corresponding to that is C translation plus C rotational plus C vibration. The specific heat we have to consider, then to calculate it, we have to consider the degree of freedom. Okay, since always is associated with some constant, and that constant have to be expressed in terms of degrees of freedom. So specific r upon 2 per degree of freedom will be there, since according to translation to dumbbell shape arrangement you have to consider. Then there are r upon 2 degrees of per degree of freedom CE, and if you use this one, so for translation there are 3 degrees of freedom, for rotational 2 degrees of freedom, for vibrational 2 degrees of freedom. Okay, as dimensions, and if you use the r of this degree of freedom, then this value will give you the different values. So, but we know that with respect to the change in temperature, all the motions will be held. So that means at a low temperature, only translation is possible. At some higher temperature, rotation is possible. At another higher temperature, what happens? All are possible. So accordingly, we can go on adding and adding, and we can have different values of CV. First, only due to translation, that is 3 by 2 R. Due to rotational, that is 5 by 2 R. Rotational plus translation, and due to these, 7 by 2 R. Okay, so depending on the temperature, specific will be different. So students, here in this particularly thermodynamics part, now we have to move towards statistics. It took a lot of time in thermodynamics, since most of the questions are there from thermodynamics, since as this is the basic FY level, as well as studied in earlier classes, and the course is also there at TY level. So the number of questions in NGP from the thermodynamics, and some questions are also there from the statistics. Okay, so we have to move ahead towards the another course, that is statistical mechanics. Okay, so what is the statistical mechanics? So in this case, these are the important topics like the probabilities, then ensemble, canonical ensemble, mechanical ensemble, grand canonical ensemble. So but still, as a statistic, we have to calculate the probabilities and all other physical parameters in terms of statistics. But the systems under considerations are the physical systems. So we have to move ahead. So the important topics, as I told you, is probability, then ensembles, the canonical, microcanonical, grand canonical, or microstate, macrostate, partition functions, energy, the number of molecules, chemical potential, Maxwell-Boltzmann distribution, Bose-Einstein distribution, Fermi-Dirac distribution, Dirac-Addition, and Stephen's law. So these are the important topics and questions will be asked in the different competitive examinations. Okay, so let's move ahead and see some reference books which are based on the statistical mechanics. It can be referred for this particular course. So the Fundamentals of Statistics and Thermal Physics by Frederick Wright. It's a very significant book. Most of the teachers and faculties are using this book to taught statistical mechanics. Then the Statistical Mechanics by R.K. Triad. Fundamental of Statistical Mechanics by B. Lard. This is also a very good book. Then Introduction of Statistical Physics by Silo R. Leon. Statistical Physics by Mendel Franz. Introduction to Statistical Physics by Hong Pearson. Statistics and Thermal Physics and Introduction by Michael Hong. These are for foreign authors also. You can use this particularly Wright book, Lard book, okay. And it means language is simple, that one. Next is the probability. So let's start this particular course. So the first one that we have seen, that is a probability. So what is a probability? It's a very simple one. You are studying for any competitive examinations. We have a number of questions in probability. Okay, though it is not based on physics also. So probability is a general thing. So some kind of questions right there. So the question is that 12 balls, each color, red, green, blue, and yellow, are put in a box and mixed. If 3 balls are picked at random without replacement, the probability that all 3 balls are out of the same color is 3 balls are required of the same color. Okay, so first that we have to find the total number of ways of drawing a 3 balls. Okay, so first we need total number of balls, right? The probability, that means maximum possibility. So 12C3 ways, that means 12 balls are there, okay, and out of which how many required? 3. So 12C3 ways, and you use this combinations formula, that is 12 factorial upon 12 minus 3 into 3. So 12 minus 3 factorial into 3 factorial. That's n minus n factorial into n factorial. So 12 factorial upon 3 factorial into 9 factorial. That gives you the total value is 220. Now the next is what? The question is that 3 balls are picked at random without replacement. Okay? The probability of 3 balls are of the same color. So 12 balls are there, 3 each of colors. So 3 balls of red color, okay, 3 balls of green color, 3 balls of blue color, and 3 balls of yellow color. That means same color ball only is one is of red, one is of green, another is of blue, and another is of yellow. That means 4 possibilities are there. That means the same color ball will appear. So that is equal to 4. So the probability that 4 color ball will appear on this particular drawing is that 4 upon 220. So that gives you 1 upon 55. That gives you 155. Okay. Now the next one, that is first order and second order phase transition. Okay. So if you have to study the statistics, you must know the phase transitions, since we know that thermodynamic state is changing from one phase to another. So that is defined by the Gibbs free energy, and it is continuous. There it is discontinuous. Here you consider Gibbs free energy, and its first derivative is continuous. Here first derivative is also continuous. Gibbs free energy, but second derivative is not continuous. These are some examples of first order phase transitions and some physical things like Lasker's electron relativity equations and all. These are the examples of second order phase transitions. I'm not going into details of that. Okay. So let's move ahead. So particularly the first order phase transition, based on it, one question, that is properties like of first order transitions are discontinuity in entropy, discontinuity in volume, discontinuity in derivative of Gibbs free energy, or involvement of latent heat, a property associated with first transition. So if we go towards the upper slide, all the properties are there here. So, and these all properties are associated with the first order transitions. Okay, so we can say this A, B, C, D are the characteristics of first order phase transitions are these changes in the molar entropy, molar volume, Gibbs function, as well as with the discontinuous slope. Okay, since the slopes are shown some different, okay, though you cannot read, still it's okay, since actually just you have to see the nature of the slopes, discontinuous one. Okay, since here, they are not the continuous one. So all things are there. for the first order transition. Now let's move ahead and see about the phase space. So how the phase space is different than your normal coordinate system. So particularly if you have to consider the phase space, then that is nothing but it consists position and momentum space. Okay. So three coordinates for position space, three coordinates for momentum space, and this combination of position and momentum we call it as phase space. Okay. So volume of a single phase cell, we can say data is a volume. Suppose this H is phase space, this to F. F is nothing but degrees of freedom. It means you have to calculate the value of a single phase cell. Then this value is calculated using this degrees of freedom and the available phase space. Okay, and allowed volume of phase space. Again, we may write this data in terms of what d cube q into d cube p is the integration of both of these. So this q represents the position coordinate and p represents the momentum coordinates. Okay, and in terms of this volume, this d cube key is nothing but the volume, and this d cube key can be represented in terms of 4 by 3 pi cube. Okay. And now, in case of non-relativistic free particles, in dimensions, 2 dimensions, and 1 dimensions, we can have a different magnitude or different values for this value. D tau, this is this 2 dimensions, this h raised to 3, this is degrees of freedom are 3, right? F represents the degrees of freedom. So here they are 3, so it is 3. Here it is 2 in 2 dimensions, so it is 2. Here it is 1, so this is 1 dimensional. So d tau is equal to q. This is a 2, and this is a h cross. Okay, it's to 1. So this is what the value associated with these dimensions. This will be, as we have seen here, this is the 3 dimensions. It is here. In case of 2 dimensions, this is not a value component, but is or in case of 1 dimension, it is 2p. One is along this, another is along this. So we can say that it's a 2p in the basis. So these are different, particularly we can say the value components, or we can say the omega now. Omega represents you the accessible states. So omega E, suppose E is there, then the accessible state associated with the energy means particularly the system having energy between E and E plus D that can be represented in terms of omega. It represents the number of accessible states of that particular property. So here we calculate these accessible states. This is the volumes, and this is actually the degrees of freedom, that is h raised to d tau, of which this volume is accessible. Suppose now omega is equal to what? 4 pi p pi semi raised to cube upon pi cross cube. So just we can substitute the value of p is equal to what? We know that in classical it is p is equal to equal to p square upon twice m. So this is a square root. Here it is a square root. So just if I take one e outside here, it becomes d. So in terms of this omega e is there, so small finance change is represented in component, that is d, and out of 1, this is square root. Okay, so you can imagine this is 3 by 2. So this becomes 1 is coming here, so remaining is here e raised to 1 half, or here it is 2 is going here into 3 by 2, here it becomes 2 pi p. Similarly, here twice me cross square, here it is now 2 dimensional, so square becomes square root of twice me square goes out, so it is here in 1 dimension, it remains p as that is square root of twice me. So accordingly, we calculate the values of accessible states, and we can write here in terms of that, or we can plot the accessible state here GE, e raised to 1 half in 3 dimensional. Okay, so here it is in 1 dimension, e raised to 1. Sorry, in 2 dimensional, it is e raised to, particularly here e raised to minus 1 half. So number of accessible states in this space can be plotted just like this. Now let's move ahead and see some examples based on it. So here is this 3-dimensional space that we called as fixed space. This is the 3 dimensions of position, 3 dimensions of momentum. And accordingly, he is questioned that the number of microstates to a statistical system in energy range E to E plus D is proportional to what? So particularly, we know that the microstates are nothing but the in which we can determine this particular momentum. physical space and momentum parameter we can express. So it is the we have discussed earlier slide. So it becomes e raised to 1/2 in 3. Okay. Now Maxwell-Boltzmann statistics is the classical analog. So particles are identical, distinguishable. That we call as Maxwell-Boltzmann statistics. It utilizes classical results of Maxwell of distinguishable of molecular velocity and Boltzmann theorem held at a low temperature. Okay. Then this is on some probabilities, number of microstates for accessible microns on total number of microstates. These are some formulas now related with this Boltzmann. Entropy is related with it, that is equal to kn of omega, that is decimal state omega we can say, and in terms of that entropy can be expressed. Then this is another physical answer, that is accessible state in terms of this particular raised to ni for Maxwell-Boltzmann. For Bose-Einstein, this is the formula, and for Fermi-Dirac, this is the formula. Okay, we'll see these examples. Okay, so here is one example. Is that we are not going in theory since we don't have too much time for that. So the question based on this particular volume is, let's have some example. The number of ways in which an identical boson can distinguish into energy levels. Okay, so number of in which n identical bosons can be distributed in two energy levels. So Gi is given, that is two energy level, and just substitute that values. So that gives the value is n plus, right? So we can say we can calculate the particular value using the magnitude of Gi, that is n plus 1 factorial upon n factorial, and that gives you the value is n plus. Now here some other question is there, omega is there, that is n Cn. This is what we know, that n factorial upon n factorial, just probability the same one. And you just have asked the entropy kn of omega, just put the omega values, and you can write here in terms of this. Okay, let's move ahead. So another particular statistics which is associated with these particles, that is a Bose-Einstein statistics. And here important property associated with Bose statistics, that is Bose-Einstein condensation. So here the one physical parameter is introduced, that is a chemical potential. Okay, so it determines the energy absorbed or released during the transfer of particles in that particular system. So nu is equal to photon, it is equal to 0 since energy is not absorbed or released. Okay, so nu is equal to 0 for photon. But now in case of your Bose-Einstein, is equal to e raised to epsilon minus nu upon kt minus 1. This is the formula, okay, for distribution of functions of bosons. Okay, and we can have average number of particles Gi upon e raised to beta epsilon nu minus 1. We can calculate the Bose temperature using n raised to 2 by 3. Population increases. So what happens particularly if it goes down in Bose statistics? And what happens Bose-Einstein statistics? We can say then the number of particles will be there in the ground level, and that increases. Since on bosons there is not a constant, that is a principle which create a constant in Fermi-Dirac statistics. We'll see later on. So here is directly proportional to T to 3 by 2. Just post temperature, post condensation temperature is there. This relation is there, and the question is on the same one. Just put this particular given values and calculate the answers. Okay. So bosons are the particles with spin. Are the spin particles, while bosons are integer spin particles. And this is the Bose-Einstein statistics. Okay, this is a distribution of the particles. Okay, or bosons we can say. Now we have some formula related, some numerical related with Maxwell-Boltzmann and Bose-Einstein Fermi-Dirac distributions. So the question is that these are the different statistics, and then how the number of ways in which two particles can be distinguished into energy states according to these different statistics. So Maxwell-Boltzmann, I told you Gi raised to two particles, and so I can write here two particles can distinguish two energy states only. So we can say that 2 raised to 2 is 4. For both Einstein's Ni and Gi are 2, so we use this formula. The value is 3. For your Fermi-Dirac statistics, it is 2 factorial upon 2 factorial into 2 into 1 factorial actually. So it gives you 1. Okay. So Relative probability, we can calculate probability of finding particle in a safe state on probability of finding particle in different states. So in Bose-Einstein, we have a maximum probability that number of particles will be there in a large number in the same state to temperature reached. Okay, since they are not in the Paulistian principle. While in Maxwell-Boltzmann, this is the half probability, and X, that is a zero probability. That means in single energy states, both the particles will not be there according to the Pauli exclusion principle. So next one is consider two particles and two non-degenerate quantum levels 1 and 2. Level 1 always contains a particle, hence what is the probability that level 2 also contains a particle for each of the two cases? Level 1 always contains a particle, and each of the cases we need one particle, either one particle. So we know that if the particle are distinguishable, one will go here, one will go here, or reverse will happen. Or what will happen that both the particles will be there in a ground state only. But in this case, particularly, we can see in this case here that is P2 is equal to this is what two probabilities are there, so the two particles are in different levels. Total probabilities are 3. Why this level is not fixed, not particularly occupied? Since we know that first the ground state energy levels get filled, and these are the classical particles, distinguishable particles. So what happens? So both particles can be there in a single energy level. So they will go to the ground level. Okay, so probability is 2 by 3. For indistinguishable particles, what happens? This or this will become same. So this is single level, and this again becomes same. So this is what to one level of these two, so probability is 1/2. A system has three energy levels E0, 2E0, 3E0, where the excited states are tricky degenerate. Four non-interacting bosons are placed in these systems if the total energy of this boson is 2E0. Okay. So three particles are there, these different energies like E0, 2E0, 3E0, 4E0, 5E0. Okay. But what happens? The total energy constraint is that total energy associated with this particle is 2E0. So if we keep these particles in these ground states, okay, that is 0 in E0, 2E0, then how many particles are there? Particularly, we have four non-interacting bosons are there. So if we keep these four non-interacting bosons like this one, this is a, so that what happens energy is 2E0. Then what happens here? We can say this is a 2E0 is the energy. Okay, and then we can have this arrangement. So this second excited energy level is triply degenerated. That means it has three possibilities. Okay, so either this will go in this will be in this, or this will be in this. Okay, so we can say that is actually it is 3 naught actually. So it becomes now E naught plus 2E0 is 3 naught. It is 3 plus 2, I think. So this is our 5 naught, I think that is okay. So first we have to confirm that one. So this is 3, okay, 1 naught, 3 naught plus 1, 2 naught, that is 5 naught. So total energy constraint is that total energy is 5 naught. So this kind of arrangement will be possible, but the second higher energy level is excited. So that's why they are shown triply degenerate energy levels. Okay, this is again a similar problems. Okay, we'll not go towards this. This is actually it will consume time. So we'll go towards this one. So what happens? The system of five identical but distinguishable particles having energy 3 epsilon. The single particle states are available at energy 2 epsilon to epsilon to epsilon. Find the number of particles in each state. So here, these are the different energy levels. We need total energy is 3 epsilon. So we can have 4 particles at 0. One is at 3 epsilon. It gives 3 epsilon. 3 is here, 2 is here, 1 is here, and 2 is here. Again, two are there. Okay, so we can write here 3 epsilon energy. So accordingly, we can see this omega is equal to 5 factorial, that means 5, 20, 10. So we can have total 35 possibilities. So in this, we can say 5 upon 35 probability, 10 upon 35 probability, or 10 upon 35 probabilities. This is probability oriented, but energy levels are different. And the constraint is given, that is on total energy. Constraint is mentioned in terms of total energy. Now let's move ahead and see some distribution related with the photon. So the distribution function Fe for a photon is given, and what is that? So we know that for photon nu is equal to 0. Just we have seen in photon is a boson actually. So E is 1 upon exponential E upon kT minus 1. Now Fermi-Dirac statistics, so distribution of particle is given in terms of 1 upon e raised to epsilon minus nu upon p plus 1. This is a plus always. In boson it is a minus. Okay. So here we know that at a generally means Fermi energy level, that means the energy occupied at 0 degree. So we can say that is what E of E 0 at greater than or equal to epsilon f, and it is less than or equal to epsilon f, it is equal to 1. That means it is occupied. Okay, and it is what the distribution at T is equal to 0. So the Fermi-Dirac distribution function for an ideal Fermi gas is plotted as this is what the question. So how it can be plotted? So curve 1, curve 2, curve 3, curve 4. So it can be plotted in terms of curve or curve. So this is at 0 degree and it's at higher temperature. So we can plot it. Okay. Held by curve 2 at absolute 0. Okay. Let's move ahead and see some another examples. The identical spin 1/2 fermions are to be distributed into non-degenerate extinct different energy levels. The number of ways this can be done. So half spin fermions are there and they are distributed. So how you can see G is equal to number of energy state into number of degeneracy. The number of energy states are 2, that is 1. Now the number of degeneracy index of the C multiplicity is twice S plus 1. Okay. So we have to calculate it. Now S is equal to what? Half. So it gives you the value 4. Okay. And number of particles is equal to now spin. How many spins are there? 1, 2, 3. So that are 3. So 4 degeneracies are here, and it is 4 C3, that is 4 ways. So this 4 ways, upper spin, downward spin, this is upper spin. Or in reverse way, this goes down, this goes up. Or what happens? This is the upper, this is the lower, but this is upper, this is a downward. And in another way, this is downward and this is upward. So this in view, this can be seen. Consider a distinguishable to identical particles over 3 energy levels, treating the particles as indistinguishable particles. The number of ways of distribution is, so that is what we know, that they are considered distributing two identical particles over 3 energy levels. Okay, so we have to distribute two identical particles, 3 energy levels. Now what happens actually? They obey the Fermi-Dirac statistics. So we can say the number of distribution is what? Either 2 energy levels get filled, though both of them will not be in the same energy levels. Either first, second, third, or first, third. That is the 3 levels. The probability of occupation of an energy level when E minus EF is equal to KT, then how much it is? This difference is KT. Fermi level means Fermi-Dirac distribution gives you P is equal to 1 upon E to E minus EF upon KT plus 1. And this factor is KT, so just put the value that is KT. And then what it gives you? E raised to 1, that is plus 1. So this is equal to these are the values, required values. Now Maxwell pulled this particularly Fermi level is that level at which probability of occupancy is 1/2 for all particles. Total number of particles in the system is given to infinity G into T. So energy of the system is equal to what? This one. Particularly, this is just represents you. This factor is what? 0 for Maxwell-Boltzmann. This is equal to -1 Bose-Einstein, and this is equal to +1. And that gives particularly the class, okay, which we have to see, and we actually see here also. So Boltzmann distribution is this much. Bose-Einstein is having a minus value and having a plus value. The Bose-Einstein distribution is obeyed by the bosons. These are obeyed by the fermions. These are the spintric particles, we can say, and half spin particles, centric particles, integer spin. These are matter in this case, since these are the classical particles. So this is an example that choose the correct distributions for one, two, and the respective functions for both Einstein and Fermi-Dirac and Maxwell-Boltzmann statistics. So here correct distributions we have to calculate. So they have mentioned 1, 2, and 3. So 1, what it represents is, as I told you, what it represents both Einstein. This represents what it will represents Maxwell-Boltzmann, and this will represent Dirac. The similar formula is also mentioned in the other side. For we can say here 1 represents the minus 1. This is particularly we can say 2 represents the Einstein statistics, 3 represents the plus 1 represents the Fermi-Dirac statistics. Why? Since this minus 1 values and plus 1 values, this value, this denominator will increase, so total value will go down. Okay, so Fermi-Dirac is downside. This total value is denominator is decreased, so numerator will go, so total value is towards the upside. Okay, and this is what the general distribution applies in the two distributions. Okay? So that question was asked in NGP 2017. So this is again the simple questions that based on theory that in statistical mechanics, the macrostate of a system is described by the variables t and v, and the density distribution function is expressed as a raised to minus sum of t. Such a description is corresponds to macrocanonical ensemble, canonical ensemble, canonical ensemble, and uniform ensemble. So particularly in case of a T and V that is given from it only get an idea. Okay, what is this indicates that it's a transfer of matter. Here particularly we can say microcanonical ensemble and canonical ensemble. T and V is related with canonical ensemble. So the difference among it that we'll see first. So here microcanonical ensemble, it is a function of N, V, and T. It means the matter as well as energy is not transferred to the system. Okay, that means transfer between the systems will not occur in this case for the quantities like matter and energy. While in canonical ensemble, we say energy can be transferred but not matter, since N is here. So matter will not be transferred, okay, but N can be transferred. E is not here. In grand canonical ensemble, what happens? N is also not there. So matter as well as energy can be transferred. Okay, when two systems are in contact, then matter as well as energy can be transferred. Then this is the isothermal and isobaric process. So these are what how the physical system were described. This is again the Fermi-Dirac statistics. As I told you, this is the +1, both sides is -1, and this is the Maxwell statistics. So the possible values for Maxwell-Boltzmann is less than 0. Here Predict it is what means we can say it greater than chemical potential, actually that is greater than Fermi level but less than 0. So it is in case of Fermi-Dirac. So it is what positive value. So denominator is large in magnitude. So it is a less in magnitude overall factor. So this is the Fermi-Dirac one. And in case of both sides, it's less than 0. So what happens? We can write here it is the highest one. So let's move ahead and see symbols here. Again, the different parameters associated with them. That is microcanonical ensemble, canonical ensemble, and grand canonical ensembles. So what is an ensemble? Basically, as I told, okay, so there are collection large number of systems that are microscopically identical but microscopically different. So here, the different microscopes, these different physical parameters are there. Not the transfer of energy will occur or not with the surrounding. We can differentiate them in terms of microcanonical, canonical, or grand canonical. And here in thermodynamics, we can have S is equal to UVN, that is KB ln of omega. F is equal to TVN, that is minus KBT ln of Z. Or phi is equal to T nu, that is minus KBT ln of Z. Okay. So Z is what? A partition function. So what is a partition function? Basically, it determines the statistical properties of a system that are in thermodynamic equilibrium. So this we call as partition function. So omega is number of states. So these are some equations which can be developed using this particularly different physical parameters. Here they have shown in case of microcanonical ensemble. That is what number of particles are same in everywhere as well as energy is same. Here canonical ensembles, we can say the same, but energy is different. So they are some are faint. Here, energy and as well as particles are different. Okay. Some are faint, some are particles different. Here also we can see the different variations according to the part of the system. So this is what the party questions related with the partition function on bosons and fermions. In case of two particles, each of which can occupy only one energy level, in zero and epsilon, what happens? So we have two particles. Classically, we can say they will go into the AB-like systems, okay? And this partition function can be represented in terms of this, okay? So 1 and 2 e raised to 0 states, okay? So fermions, if they are particularly, then they will be distributed according to this. Bosons will be distributed according to this, and can have different partition functions of the different bosons. I will not go in details since actually time is over. So the distinction between fermi and Bose-Einstein distribution arises to what? That is what the question last one. So that we know that spin, because the spin distinction between the Fermi tract and Bose-Einstein arises due to spin or Pauli exclusion principle or indistinguishability or wave function. So we know that what happens particularly spin of the particularly different particles are different. Since spin fermions are a spin on a particle, bosons are integer spin particle. Pauli exclusion principle is obeyed by the fermions, while that is not obeyed by the bosons or Bose-Einstein distributions. Or wave functions, we can say they are the different wave functions. Bosons have symmetric wave functions, while fermions having anti-symmetric wave functions. Then what is the similarity in these two distributions? That particles are indistinguishable. In bosons and in fermions, particles are indistinguishable. While in case of your classical or Maxwell-Boltzmann statistics, particles are distinguishable. So with this particular basics of thermodynamics and statistics, I would like to conclude here and stop here. So thank you. This is our college. You can visit our page.
Okay.
Now,
Yes.
I
Thank you, Dr. Kakade, sir. Thank you. It was very nice
yes.
feast for all the students. Almost you have covered all the topics or the subtopics of this particular course. That is these thermodynamics and statistical physics. Of course, the entire subject is very vast. There are several courses, at least 2-3 courses that comes under undergraduation, and it is very difficult to cover almost every topic from that particular course in 1.5 hours. So doesn't matter. Now, shall we go for the questions? Shall we go for the questions, Kakade sir?
Yeah.
Yeah. Now there is.
Yes, no problem.
Yes. First question is from Vaibhav M. Tamde. He asks, while exhaling air through ha, okay, lip movement, ha, like this, lip posture feels warm air. Okay, when we feel ha, or when we make a posture ha, air is found to be warm, and when we make a lip posture hu, like this, at that time this air is feel cool air. So what is this particular effect?
Yeah, so the question, they ask the questions like, while exhaling air, how we feel the warm air, and while inhaling, we feel the cool air. It's a very good questions. I think the answer is that since we exhale, then water vapors comes
No.
up. So humidity is the reason.
I will answer, sir. Sir, I will answer this. I will answer this question. This is a simple.
Your
This is called as
voice
Joule
breaking.
Thomson effect. This is a Joule Thomson effect. When air is expanded, okay. So when air is expanded, that means that is called as throttling process. So some of the students may be knowing that This is called as a throttling process or Joule-Thomson effect. When air is expanded from higher pressure to lower pressure, in that case there is a cooling effect. And when the air is expanded or is exhaled into the region from low pressure to high pressure, in that case there is no temperature increase. Therefore, when we say ha, the air is hot one. And when we go for hu, in that case, there is an expansion of air from higher pressure to lower pressure. And in that case, there is a Joule-Thomson effect, or that is called as throttling process in thermodynamics. And because of that, this here air appears to be cooler at that particular gesture. That's a very nice question. It's a very applicable question. And that is what a Joule-Thomson effect when we see here. Okay. The next question is, why environmental, again Vaibhav Tamde, why environmental temperature increases if we keep the fridge door open? Our fridge that we use in household, its temperature goes
They're very
increases.
simple things. If you open the door, then warm and moist ambient air mixes that particular cabinet of the door, and I think due to which there is small rise in temperature since moisture number increases with the number of the opening.
No, actually, environmental temperature increases. It is never like that. When fridge is functioning or working, in that case, it works against the atmosphere. So it takes heat. It gives out heat from inside. Whatever space inside the fridge, that heat is taken up, and that heat is given to this atmosphere. That's why the atmospheric temperature increases, while the fridge inside the or the space inside the fridge that gets cooled down. So this is what, when the fridge is open, its door is open, I don't think this will happen here, because in that case, every time this fridge is not going to work, and this will not cause any change. But whenever it is closed, one fridge is working, in that case it increases outside temperature and not the inside. Now inside temperature decreases, whereas outside temperature increases. That should be the question. Actually, it had been asked there. Now request for other students, those who are live here, please go for your questions related to this NGP examination that will be solved by Dr. Kakade sir, live here. Please go for your questions. In
Yes.
private chat, yes. There is one more question by Jayesh. Actually, already these two questions by Jayesh as well. What is the difference between heat engine and the external work done? What is the difference between heat engine and the external work done?
I think the heat source is separated. Heat source is different in that case. Means external heat engine, they're generally steam engines.
What is difference between
And
heat engine and
they are differing from the combustion engines. Yeah. They are differing from the combustion engines. The source of heat is separate one.
So actually these two concepts are different. One, heat engine is the device, and external work done can be a system. That can be a system. So external work done can be anything.
Yeah, see, actually, external work done can be anything. That is what the reason. This question is not particular one.
Yeah, no, not particular.
Heat engine. Yeah, the question is not specified particularly.
Yeah, not specified. Okay. Only I think these are only 3-4 questions. So already we have taken 2 questions. There is, I think, one more in this. What is the difference between heat and temperature? This is again by Mr. Vaibhav Tamde.
What is the difference between heat and temperature? Particularly, heat is the amount that means we can whatever the amount of heat which we are giving to the system, that is measured in terms of dq. While temperature, we have to see that internal characteristics of the system, and heat is it is a physical quantity which we are giving to the systems or evolved by the systems. While your temperature is associated with the internal energy of the system, and that the characteristics of the internal energy of the system. So if you heat, then their internal energy, it will be absorbed by the system That's why its internal energy will increase, and that will rise in temperature, and the remaining will be utilized to do a work. So it is not directly the internal energy, or it is not directly related to the internal energy, but it is related with the work done also. And first, but temperature rises of that particular system, and internal energy is the characteristics of the system, not the heat. If
Yeah.
heat is given, then internal energy of the system will change. So it is external, particularly you can say the physical quantity which we are giving to the system or absorbed from the system.
Yeah. And temperature is the
And
degree of
measuring
hotness. It is the measure of
how
hotness.
much heat is given in terms of and all, but we are not measuring the heat in terms of how much temperature of heat is given and all that.
Yeah.
We are measuring in terms of quantity, since it is a quantitative term, while temperature is a qualitative term.
Okay. So I think there are no questions now. All these questions asked by Jayesh, he says that he received these questions from other communication means, doesn't matter, but these questions were nice, good, and very good one. So this is what the question that was asked. Then one more is by Vaibhav Tamde again. I am FY students. Will college open till NGP examination date? This is not a question to be answered here. It is not in our hand. So you better inquire into the university. That will give you correct answer of this particular question. Okay. So I think the questions are over here. So now Joshi ma'am is not there. So I say let me go for thank you. Yes, Joshi ma'am is there. Ma'am, please go for
Yes.
vote of thanks.
Yes, thank you, sir. I would like to thank today's speaker, Dr. Sandip Kakade, for his nice explanation and covering all the scope of this statistical physics. It is actually a difficult subject to understand, but he has done it in a very nice manner. I would like to thank SP College Science Association and Principal SP College for making this platform available to us. I thank Professor Bharat Kangude, President of Indian Association of Physics Teachers, RC08C, for arranging this particular lecture series. I would like to thank all of the student participants for their registration into this particular event and attending all these lectures. These lectures must be surely beneficial to you while going for this NGPA exams. I would like to thank all of those who have helped in arranging this series. So with this, we end the session for the today. Thank you.
Yeah, thank you. And once again, all of you, tomorrow, please remember, session will start exactly at 6. And the tomorrow's topic that will be discussed is classical mechanics by Dr. Bagode Madam from Vidya Pratishthan College, Baramati. So I hope all you will be there to understand the basic important concept from classical mechanics. With that, we end here in today's session. Thank you and good night, you all. Thank you all.
Thank you all.
Please.
Thank you, everyone.
Yes.
Thanks.